All right, so we start with the R coding of multivariate analysis. So do you have the idea about the Google Colab? Google Colab. So if you are doing a coding either in Python or in R software, so if they, what happens, they provide the packages, okay, in Python or in R. So that's why they need to develop their software day by day. Okay. So what happens? Some packages are, and what happens with all of you, with all of us also, we install the R software or R Studio once or Python once we just install, and every single time we cannot upgrade it, right? Most of the time we are not means what happens every single time you need to uninstall it, then again you need to download and install it. So we don't do that most of the time. So in that one, if you are not going to update your R software, so what happens in that case? Sometimes your some packages will not work in R programming or Python. Like here, if I am having this code, okay, this particular code I am having here. In this one, I are you able to see this R code? Yeah. Okay. Let me increase the size. Okay, so this is a one package ICSNP. This is for the Hotling T square. Okay, I just run this command here. Now it is showing the error. Loading required the ICS error package or namespace load failed for ICS. Okay, and they are saying that after that ICS could not be loaded. One error, and R is this ICSNP and ICS are built under the version of 4.4.3. All right, which version I am having right now? 4.4.2. Just so I cannot do it again and again, right? So at that time we have a one option, that is Google Colab. You simply type Google Colab on R, so on your Google Chrome, and open this one. All right. So how it works? So here, whatever the previous files are there, it will show you here. And if you want to work on some new file, it you can open the new file from here, new notebook. Okay, so it will open like this. All right. So after that, what you need to do, it will provide you the Google Gemini to help. Okay, in your code. So we don't need that one. So after that, what you can do here, automatically when you will open, it will do the coding in Python. So you need to change it into the R first of all. So first of all, you need to connect it. Okay, you need to click on the connect on the right hand on the top. So when it will connect, it will take few seconds to connect here. Okay, it connect RAM disk. It should appear here, RAM and disk. Okay, it is appearing. After that, you will come here on the runtime. Okay, and here you need to click on the change runtime type. Okay, you will click here. So automatically, if you will see, you are finding here Python 3 is there. Right. So you need to change it with the R. Okay. And simply save it. You don't need to do anything else. Okay. You don't need to click on any other option. So now whatever the code you will run of R programming, it will run here. Otherwise, if you will start write the code of R programming here, it will not run. It will show the error. And the best thing about it, it is directly connected with your Gmail account. Okay. So whatever the code you will write here, it will automatically save on your Google Drive. And when you will reopen it, okay, whenever you will reopen your code, it will reopen with the outputs. So you don't need to run it again and again. So suppose you have very heavy coding code, means that are going to take the number of hours to run. Okay. When we just write the code in the research, Sometimes code take the 45 hours, 50 hours to run. Okay. Sometimes it take the 7 days also, day and night. Sometimes. So at that time you cannot run it again and again. So what happens when you will run it here? So it will save. So if just I just see here in the file, open notebook. If I want to open some my previous code, so it is there. So suppose I have this code previously. I'm going to open this one. So you will see here, this is my code. Okay. And this is the output of this particular command. This is the command and this is the output here. Okay. This is the model that I applied. That is the command that I applied. And corresponding to this is the applied. Okay. So this is the output of my command. So I didn't run it. Okay. And I saved it in 2024. If you just see here, the name of the code is FDP 2024. So it is still saved. Okay. So I don't need to run it again and again. The graphs is as it is. So I don't need to run it for the graphs and everything. So that is the very safe way to run the R codes. If some packages are not working, so you don't need to be worried about it. So you don't need to uninstall your software, R software or Python software, and then again you don't need to reinstall it. You simply work here and it will be saved. Okay. So now we will go for the our R code. And there is one thing, how you will write the code here. You will get the boxes. Okay. You will get the boxes here. This is a one box. Okay. In this box, either you can write your entire code or you can split in your code in the boxes line by line. Okay, like what I did in this particular box, what I just give the install the package IC, SNP and Hotlink. I want to install these packages. When you install the package in R, what you do? You need to select first country. Country names appear na when you install the packages. Yes or no? Right. Then after that, in the second time in the second box, again after that the packages come. Right. So list of the packages appear after the country names. Right. So what you do here you don't need to mention that all these things. You just simply write the command, and you can write the code, entire code in a once. Yeah. If you want to add the line here, either you just put enter, or when you will come here, so it will come up, it will appear. When you will come in the middle of the box, in the last of the box, when you will appear in the middle, so it will give you two options. You want to add the text or you want to add the code. So when you will click on the code, so another box will appear here. So here you can write any code, whatever the code you want to write. And if you want to delete it, delete this particular line. Then the other code will remain as it is. Okay. So what you can do, you can run all those in a once, but other boxes will run when this box will completed. Okay. So now I need these two packages. So I'm going to install these packages. So to install the packages, the command is install.packages. We are because if you want to install only one package, so you don't need to put C combine. You just simply in the inverted commas, you just simply write hotlink and run it, so it will install. But if you want to install more than one packages, so in that case you need to write C combine, and inside the bracket you need to write the all the packages name in the inverted commas. So I'm going to run it. So now it is running. And I can run this also at the time, but you will see here the dotted circle will be there. It means it is waiting to complete first one. When first box will complete, first command will run. After that, the second command will run. So now second command is already run. So it is showing that installing the packages. Okay. and it is installed. If it is the red green one, so it is installed. Otherwise, if it is red tick is there, so it is not installed at all. Means some problems are there. So here, when you will run the code here, so this is the code for one sample Hotling T-square test. So what we are going to do, we don't need this one. I just take it from my previous code, so we can delete this line. Okay. If you don't know, we use this command PAR mfrow to split the window of graphical representation in R. Okay, so when you run the code, you run any plot in R. So in the window, in the graphical window, only one plot appear in once. When you will run the another uh, program for the graphical representation, so it will replace the previous one. But if you want all of them together in a one window, so you need to split that window in a matrix form. Okay, you need to split that in the matrix form. So this is the right now I'm going to split that my window, my graphical window into 6 by 4 matrix. Means 24 plots can appear in my one graphical window. Okay, so that is the meaning of this one. So because I am not using it here, so I am going to delete it. So when you are going to use some package in R, so you need to write library and the package name inside the small bracket, whatever the package you want to call. Because I am applying the Hotling T-square test and Hotling T-square command, this, there is a command Hotling T2. This command is basically given. Is it visible for you? No? Okay, this Hotling T2 command is available in ICSNP package. So first I need to call this package, and then set.seed is basically to fix the sample size. If you are generating the sample from the some distribution or from some uh, given data set, if you want to generate the sample. Okay, so here I have the data 20, 10.3, 0.8, 20, 5.2, 0.6. Sorry, I am going to generate the random data from the normal distribution of sample size 20 with mean 10.3 and standard deviation 0.8, and another data of size 20 I am going to generate from the normal distribution. For that one, command is rnorm. If you are going to put r in before some before any distribution command, it is used to generate the random data. Okay, r binom, r chi-square or IREXP. These are REXP for the to generate the random data from the exponential distribution, R binom for the to generate the random data from the binomial distribution. So similarly, R norm, sample size 20, mean 5.2, standard deviation 0.6. Number of columns, how many number of columns I want in the matrix? That is 2, because I have the two variables. Okay. And after that, I am going to hypothesize the mean for this is the my mean under the null hypothesis, that is 10 for first one, 5 for second variable. Okay. Are you getting this one? What I am trying to say? Are you getting this one or not? Okay. Wait a second. Give me a second. 0.8. Okay. And the second variable I am going to store generate from the mean 5.2 and standard deviation 0.6. Now I want to check that whatever the data I'm going to generate from here, so in that one, two columns will be there definitely. So that's why I'm saying n columns equals to 2 here. After that, in mu naught equals to 10 and 5. So here I'm going to introduce my null hypothesis h naught such that mu naught is a vector of mean, that is basically 10 and 5. That means mu1 equals to 10 and mu2 equals to 5, that I am assuming, that I want to test under the null hypothesis. Okay. And after that, I am going to apply the Hotelling t-square test. Okay. So for that one, inside this package, ICSNP, there is a direct command to apply the Hotelling t-square. That is your Hotelling T2. Here, what you need to provide? You need to provide your data matrix, capital X, that we store here in the matrix. Okay. And mu, in the mu, that because in the Hotelling t-square we test for the mean, right? That is we store in the mu node under the null hypothesis. What is the mean we are assuming? And then print the results. Print this one. So it will provide you the output. After that, we are going to do the manual coding. Okay. This is for the direct command. The manual coding is in n is the number of rows of x. We are going to define how many rows should be there. The number of rows should be the number of observations that I'm going to generate. So 20 rows are there in this matrix. Okay. P is the number of columns in X. How many variables are there? Two variables. So that is equals to the number of columns in matrix X. Then I will compute the X bar, the column mean of each column. So for that one, the command is simple command is there, that is call means. If you have the matrix and you want to compute the mean of each and every single column, so for that one, the command is call means. Then inside the bracket, you will provide the matrix and it will provide you the X bar. After that, I am going to compute the variance covariance matrix of X. Okay. So that should be 2 by 2 matrix. Variance covariance should be a 2 by 2 matrix because two variables are there. So that I am going to store in capital S. Okay. And after that, I am going to call that one. After that, I am going to calculate the t-square. What is the formula of t-square? That is n into transpose of x bar minus mu naught multiply with the inverse of covariance matrix. So for that one, to find out the inverse of the matrix, the command is solve, right? Multiply with the x bar minus mu naught. When you are going to multiply two matrices, the command is percentage sign, multiple sign, and percentage sign that I told you earlier, right? And then after that, I'm going to break the line with this semicolon. And then I'm going to call the t-square. What is the value of t-square? And then I will calculate the f statistics, that is n minus p divided by p into n minus 1 into t-square. That is the formula of f statistic. Then I will call the f statistics here by f stat. After that, I will calculate the p value. Yeah, so after means what is there? This semicolon means this command is completed up to here. After this semicolon, it behave like a new line. Whatever I will write after this, it will behave like a new line. Instead of introducing a new line, I can put the semicolon and then I can write whatever I want to call. So it's behaving like I am writing T2 in the next line. T2, whatever the values of the T2. Okay. So it will show there. P value after that I will calculate. How I am going to calculate the P value? 1 minus P F is representing for the F distribution. Okay. So whatever the F statistics I calculated, that is behave like a variable of F, and P and N minus P are the degree of freedoms. Okay. And then I call the P value, whatever the, so I want to run this entire command here that is given in this box. So I need to click on the play. Okay. So this is, it is run, and these are the outputs. It will split the box into two parts after that. So this is the whatever the things coming here up to here, this is coming from the hotlink T2 command results. Okay, so it is showing that the values, what is the value of t square, that is 4.1154. Degree of freedom first is 2, degree of freedom 2 is 18, that is n minus p, and t value is 0.03374. And alternative hypothesis is true location is not equals to 10 and 5, means mean is not equals to 10 and 5. That is your alternative hypothesis, two-sided null alternative hypothesis we assume here. After that, I'm just running the manual command. In the manual command, what I called the x bar, I called the s, I called the t2, and then I called the f statistics and p value. So 10.4132 and 5.61692 and so on, these are your x bar. Okay. After that, this A matrix 2 by 2 matrix, this is your variance covariance matrix. Okay. This is your variance covariance matrix. And then this one, 8.68, that is your T2. Okay. And then, sorry, this is not your T2, this is your 1 by 1 matrix. So what I called before that S, no, this is something else. Okay, a matrix 1 by 1 of the type so this is the matrix, A matrix 2 by 2, matrix A 1 by 1 of type double, what I called here. This is S, this is X bar. T square should be this one, 4.1151. Okay, this is something else. All right, and then F statistics is this. So this is the P value. And this is the F statistics, and this is the value of T square, right? This is the value of T square, this is the value of F test, and this is the value of your P value. Okay, so now you can take the decision based on your P value. What will be the decision here? Reject the null hypothesis. Why? 0.05, because P value is less than 0.05. Similarly, here we have the R code for two samples. So here what we are going to do? We are going to generate X from the normal distribution again. Okay, 2 by 2 matrix. It will it will be a 15 by 2 matrix. 15 rows and 2 columns. So first column is, in the first column, in the X, it is defined as X, that is X11 up to X115 and X21 up to X215. This is your first data set. Both of them are generated from the normal distribution with mean 75 and with mean 72 and standard deviation 10 and 8. Okay. And why I'm going to make another data set, that is another matrix. Here it is your, what it will be, 12 by 12. Both can have the different size, yes or no? Both matrices can have the different sizes. So here it will be y11 up to y112, y21 up to y212. This is your another data set. Here the first variable y1 we are generating from the normal distribution with mean 68 and standard deviation 9, and another one we are generating from the mean 65 and a standard deviation 7. And if you want to apply the Hotelling t-square test, in that one, what will be the null hypothesis? What will be the null hypothesis here? H naught such that mu1 should be equals to mu2. Means mu1 is basically the mean of mu11 and mu12. Mu11 is denoting the mean for this one, and mu12 is denoting the mean for this second variable x2, and mu2 is basically mu21 and mu22. That means mu21 is denoting the y1 and mu22 is denoting the y22, right? So we are saying that mu11 is equals to mu21 and mu12 is equals to mu22. All right. So at that time, we will not provide the mu here as we were providing in the previous command. In the previous command, we provide the mu, no? But this time, mu will be 0 when both of them are same. So what will be mu basically? If you say it mu, so mu will be 0 when you will take on the other side. If I am saying that h naught such that mu equals to mu1 equals to mu2, that means mu equals to mu1 minus mu2. If you are going to take, that will be 0, right? Both of them are equal. So that's why you are not going to provide the mu a here. Okay, you will provide only both data set. Okay, both matrices of the data set, and then you will call it the command result 2. Okay, here in the manual, what we will do, because we have the two different data set, so we will first n1 is the number of row in x and n2 is the number of row in y. What is the size of one first matrix and what is the size of the second variables? Okay, first variable and second variable. What is the size? What is the length? Length is the number of rows, right? And both of them are different. Okay, and p is the number of column of x because both of them have the same number of variables. So that's why either you can take number of column of x or number of column of y, both are same. Okay, so we are taking number of column of x here. So n col means number of columns. In S1 is the covariance matrix of x, and in S2 we are going to store the covariance of y. Okay, after that we will call both of them, right? And then we need to create the pooled covariance matrix. We studied the pooled covariance matrix, that was n1 minus 1 into S1 plus n2 minus 1 into S2 divided by n1 plus n2 minus 2. That was the formula, right? So this formula I'm going to use here to compute the pooled covariance matrix. After that, I will compute the difference. Okay, column means of x minus column means of y. In that one, I will compute the mean differences of the mean. Means the mean of x1, mean of x1 minus mean of x2 and mean of y1 and mean of x2 minus mean of y2. That I will calculate here by the difference of the column means. And then I will call the difference. After that, I'm calling the T2. Okay, the Hotling T square. That is N1 into N2 divided by N1 plus N2 into the same formula that we were using earlier. Instead of x bar minus mu naught, we are going to use the difference. Transpose of the difference of column means of each matrix, then inverse of the pooled covariance matrix into difference of mean of both matrices, and I will run it. Okay, so this is my T square here, 7.92. Difference degree of freedom is 224 and p value is 0.002273, and alternative hypothesis, both of them, the difference is not equals to 0. Okay, and this one is test statistics is 16.517, number of degree of freedom 2, number of degree of freedom is 24 that I called here. Okay. And then P value is 0.002273. This is your variance covariance matrix. Okay. First, this is your second variance covariance matrix. And this is the pooled variance covariance matrix. And after that, this is your difference of the mean vectors. And this is the value of your t square by the manual. Okay. Yeah. Result 1, result 2, yes. Result 1 is for Hotling t square for the first program. Okay, this is your result 1. Result is basically for your first program. Here I am not using the result 1. Okay, sorry. So result 1 is for with the ICNP package, and result 2 is for the Hotling package. Sorry, I forgot that. And when you are going to apply the Hotling t square with the Hotling package, the command is hotling.test. Okay, sorry, I forgot that one. Okay. Yeah. Yeah. When you are the two data sets, so what we are basically assuming in the null hypothesis that mu1 equals to mu2 means both of them are same. If both of them are same, so the difference will be 0, right? So that's why we are not giving a matrix here, that vector, mean vector we will not provide here because that is 0. We are assuming. Okay. If you are giving, then you need to provide 0, 0. Oh. 0, 0. Automatically it will assume 0, 0 if you are not providing it. All right. So that is the command. That is the code for your that one. What we call it? Hotling t square test. Okay. Now we will talk about the principal component analysis. Okay. Is it visible? So here we have the first example from your PPT. The PPT we have for that one, principal component analysis, right? In that one, we have the example for the insurance claim data, right? So in that one, we had the age 25, 35, 45, 55, 65, and claims 2, 3, 4, 5, 6. Okay. And the premiums, okay, $800, $1,000, $1,200, $1,400, or $1,600. That are the claims that we are taking, premiums that we are assuming here. Okay. So in that one, first we are going to store the data in these three vectors we are defining. After that, we are going to combine all these three vectors, data set vectors, in the data frame. Okay, so the command is data.frame. Here we are going to store age, we are going to store in the age, we are going to claim into the claims, and premium we are going to include in the claims. Premium, sorry. Okay, so I'm going to run all these three and I will check what is the results outputs I am having. So this is my data set right now. Okay, why we are not storing them in the matrix? Why we are storing in the data.frame here? Hmm? Because when you just give the data set, you are going to store it in the matrix. So columns you will provide, suppose you are providing these three columns. Age is a one column, claims in a second column, and premium in the third column, and this is the matrix. So at that time, what happen? All three have the different properties. Means age is different variable. In the age, you can store the different observations. In claims, you can store different observations. In the premium, you can store the different observation. But means all three have the different characteristics. Right? This is the dollar. Okay, this is the number of claims. This is the age in the years. Right? Correct. Means all three have the different characteristics. But when you create the matrix, in the matrix, all the variables, all the columns should have the same characteristics. Okay, so that's why we are introducing data.frame here. After that, I am using the PCA, using the covariance matrix. In that one, I'm just storing the my principal component, first principal component in the PCA1, and to run the principal component, the command is PRCOMP. Okay, it will perform the principal component on my given data set. Okay, so first I need to provide the data set, that is data 1. Okay, I store the data in data 1, right? And after that, I'm going to say that center equals to true. Because if you just remember, when we were introducing the principal component, what was the formula of the principal component? If PC1 was, or that we said Z1, that was V1 into X1 minus X1 bar, means first first column of the data set and their mean minus their mean, plus V2 into X2 minus X2 bar. Correct? Yes or no? So and so on. Where V2 and V1 was your eigenvectors, and this is your centered value. X1 and X2, X1 bar, when you are finding this one X1 minus X1 bar, that was the centered value. So means you are subtracting each variable with their respective mean. Yes, so we need to do that. So that's why we are going to do the center equals to true. But after that, we are saying scale dot equals to false. What it means, we are not going to scaling to get the variance 1. Okay, variance can be have the different values. So we are not going to scaling in such manner that principal component that should have, means whatever the data we have, that should convert it with the variance 1. Okay, so I'm going to run this command here. Right. Now, to find out the summary of the PCA, I have the command is summary PCA1. It will provide you the basically the variance of each principal component. Okay, standard deviation of each component, proportion of the variance, how much proportion of the variance each variable is taking. Okay, so first principal component is taking the all the variance, and here cumulative proportion is there, that if you remember that we find out. Do you remember that one? The formula of the proportion of the variance that we find out earlier. We were saying that proportion means variance. What is the standard deviation basically? Standard deviation is the square root of the eigenvalue. Okay. Standard deviation is basically equals to the square root of the eigenvalue. Okay. Lambda 1, lambda 2, and lambda 3. Three eigenvalues were there. And the proportion of variance. Okay. Proportion of the variance is basically lambda 1 divided by sum of the lambda I. Okay, that is called as the basically proportion of each variance. Okay, lambda 2 divided by summation of lambda I, lambda 3 divided by, sorry, summation of lambda I. This is all three values here. Okay, cumulative is basically lambda 1 divided by summation of lambda I. This is your first cumulative proportion. Second proportion is basically lambda 1 plus lambda 2 divided by summation of lambda I, means all lambda 1, lambda 2, lambda 3. And third one is basically lambda 1 plus lambda 2 plus lambda 3 divided by summation of lambda I and others. So here, that's why it is 1. Okay, and this is also 1. Because lambda 1 is already sharing the complete one. Okay, this is your eigenvalues. Okay, here now what is your eigenvector? This is your eigenvector v1, v2, v3. Okay, so it is showing that with 0.99 premium have the highest uh, loading. Okay, and with the negative sign it is have the negative loadings v2. Okay, so now we will check the eigenvalues that we are having. These are the eigenvalues of our principal component here. Now we just check the PC1 score $x. Do you know why we are using this one dollar sign? Okay, sorry, I forget to tell you that in the PCA1 all the results are stored in the PCA1. Eigenvalue, eigenvector, and other things, everything is stored in the PCA1. So if you want to extract any particular property or any particular characteristics from the your PCA1, okay, any one, so that is you need to put the dollar sign, and after that the thing that you want to extract, you need to write that command. So for the eigenvalue, the command is rotation in R. Okay, to extract the eigenvalue from the principal component, the command is rotation. So dollar rotation will provide you the eigenvectors. Okay, and after that, if you want to extract the eigenvalues, so you need to write the standard deviation HD EV square of that one. That will provide you the eigenvalues of the principal component. So you need to write dollar standard deviation square. Okay, so that's how I get the values here. Okay, you can store it in some other also like this eigen value. Okay, so now your eigenvalues of your principal component are stored in the eigenvalue. So if you will run it, so what will happen? It will not show the result. It will just store the eigenvalues in the eigenval. Okay, now you need to call eigenval. So it will show you the eigenvalues. Okay, now your eigenvalues are stored in the eigenval. So what is the score here of the principal component? Okay, these are the score of the principal component with respect to the each value. Okay, so first principal component vector, second principal component vector, third principal component vector. If you remember when we solved numerically the example in the class, so when I find out the eigen principal component, I found out the vector of the first principal component. Yes or no? Do you remember that one? I find out first. I find out the variance covariance matrix of the centered data. Then I use this formula. This one, eigenvector into the matrices centered data variable. this formula I used, right? And corresponding to that, I find out the first principal component. Do you remember that one? So it is finding directly all three principal components. Okay. Now I will see the scree plot. Scree plot is the basically the basic plot of your principal component in the principal component analysis. Okay. So this is your principal component analysis scree plot. So in scree plot, what is shows that in the x-axis it shows the number of variables. Variable 1, variable 2, variable 3, because we have the three variables only. And on the y-axis it shows the variance. Okay. So this is called as the basically the elbow rule. Okay. Where your elbow is going to be moved. Okay. So if you just see, your elbow is going to be turned, okay, or basically move at the point of variable 2 here. Okay. So before that, till your elbow is straight, before that, you will consider all those variables, and where your elbow is going to be basically move a bit, you will leave all the variables that, and after whatever the variables are there, you will leave all those variables. So here you will see that your elbow is basically okay. So your curve is basically bent here. So your elbow is basically bent here. So whatever the variables before that, you will consider those principal components. So because here, if you just see 2 and 3 are having the variance almost 0. Okay. Only first variable having the variance 1 into 10 raised to the power 5. Okay. The meaning of this one, 1e plus 0.05, meaning that 1 into 10 raised to the power 5. Okay. Meaning of this is 1e plus 0.5 means basically 1 into 10 raised to the power 5. Sorry, 10 raised to the power 5. Okay. So this is having the highest variance. So you will consider only first principal component for your further study, because it is sharing the, or it is capturing the entire variance. Okay. That is your principal, basically principal component analysis. So we are not going to consider the second and third principal components. First principal component is more than enough for us for the further study. Okay. For the further study, only first principal component is enough for us. We don't need the PC2 and PC3. Okay. When the times will up, please let me know. I don't have the watch. Time's up. Okay. So others I will discuss in the next class. Okay.